Hello everyone, welcome to Enviro Pioneers. In this video, we are going to discuss about the spatial, spectral, radiometric and the temporal resolutions in remote sensing. As remote sensing is the acquisition of data with the help of non-contact sensor, this acquisition depends upon what information is needed and how much detail is required and how frequently we need that data. Accordingly, the different sensors may be used and these sensors can be placed either on the ground-based platforms, airborne or the spaceborne platforms. So one of the important aspect in the remote sensing is the resolution of the data which is collected by the sensor. So this resolution is defined as the level of detail or accuracy of the information which is captured by the sensor. So how much information is acquired and what is the accuracy of that data that comes under the resolution, and it varies from sensor to sensor and also depends upon the satellite orbit configuration and the sensor design. And this is very important in remote sensing because it determines the applicability of the data, because different data have different resolution and each of the data with different resolution they provide different level of details. So depending upon what information or which type of data we require, accordingly the sensor can be designed or the data can be procured or it can be downloaded. In remote sensing, the resolution is defined mainly in four terms: spatial resolution, spectral resolution, radiometric and the temporal resolution. Spatial resolution is with respect to the pixel size or the instantaneous field of view. Spectral resolution is related to the bandwidth. Radiometric resolution is related to the intensity and the temporal resolution is related to the time. So we will discuss one by one these in detail. Spatial resolution is defined as the measure of the sensor's ability to capture closely spaced objects on the ground and their discrimination as the separate objects. This spatial resolution, it depends mainly on the instantaneous field of view of the sensors, and it defines the size of the smallest possible feature that can be detected by each sampling unit of the sensor. So here in this diagram we can see the suborbital platform, suborbital and the orbital platform. If we talk about this suborbital platform which is placed at the height h above the ground level, this is referred as the instantaneous field of view, which is the solid angle through which a detector element is sensitive to the electromagnetic radiation at one time. And this solid angle, when it is projected on the ground, here it is referred as the ground projected instantaneous field of view, and this is the diameter of the ground projected instantaneous field of view. There is another term, field of view. So as the height of the platform is increased above the ground level, the field of view, that is the total view angle of the sensor, it increases. So when we are saying the platform, it is simply the vehicle on which these sensors are placed. So here we have three examples and we can see that as the height of the platform is increasing, the total view angle or the total field of view, that is increasing. Here also we have the second example, and we are having two platforms. One is shown in yellow and another is shown in the blue. We can see here that the total field of view is increased in case of the blue one, which is placed at the height of h1, that is more than the h2. This field of view is different from the instantaneous field of view because it defines the swath, that is the total distance on the Earth's surface that a particular sensor can capture from a certain height. So here we can see two examples. This is for the whisk broom scanning and this is for the push broom scanning. If you remember, whisk broom scanning is the case where we have the scanning mirror which rotate to and fro to capture the data, that is across the track. So the angular displacement in which this scanning mirror is getting rotated to and fro, that is referred as the field of view, and with respect to this field of view, how much distance is getting covered on the ground, that is referred as the swath width. एक सिंगल मूवमेंट में ये जो सेंसर है वो कितने दूर के लिए सेंसिटिव है या कितने दूर की इंफॉर्मेशन को ऑब्टेन कर रहा है, तो ये जो सॉलिड एंगल है इसको हम कहते हैं इंस्टेंटेनियस फील्ड ऑफ व्यू, and the distance which is covered on the ground, that is pixel size. And similarly in the case of the पुशब्रोम स्कैनिंग, जहाँ पे हमारे पास लीनियर डिटेक्टर एरे होता है. So the linear detector array means where we have the series of the detectors with one detector per pixel across the swath. अब ये जो लेंथ है डिटेक्टर लीनियर डिटेक्टर एरे की, ये डिफाइन करेगी कि कितना डिस्टेंस ग्राउंड पे कवर हो रहा है. सो दिस एंगुलर डिस्प्लेसमेंट इट इज रिफर्ड एज द फील्ड ऑफ व्यू एंड ऑन द ग्राउंड इट इज रिफर्ड एज द swath width. बट फॉर अ पर्टिकुलर डिटेक्टर एलिमेंट ये जो सॉलिड एंगल है दिस इज इंस्टेंटेनियस फील्ड ऑफ व्यू एंड इसका जो प्रोजेक्शन है ग्राउंड पे दैट इज रिफर्ड एज द पिक्सल साइज. It can be more clear from this diagram if we consider the sensor on this platform. So the angular displacement for covering the swath width या जितना distance हमारा ground पे cover हो रहा है उसका angular displacement जो है this is referred as the field of view and on the ground it is referred as the swath width. And for particular detector और for a single movement कितना ये एंगल डिटेक्टर क्रिएट कर रहा है या सिंगल डिटेक्टर एलिमेंट की अगर हम बात कर रहे हैं तो दिस इज इंस्टेंटेनियस फील्ड ऑफ व्यू. एंड ये जो प्रोजेक्ट हो रहा है ग्राउंड पे इसको हम कहते हैं ग्राउंड इंस्टेंटेनियस फील्ड ऑफ व्यू एंड जनरली इट इज elliptical in shape. But from this ground sample distance is calculated and जो pixel overlap हो रहे हैं that is actually removed and only that part which is not having any overlap with the surrounding area that is calculated to get the ground sample distance which defines the resulting pixel size. So from the instantaneous field of view we get the pixel size and this pixel size is proportional to the instantaneous field of view and the height of the platform above the ground level. Spatial resolution is given in terms of the pixel size. So this dimension of pixel size, it is represented in meter or centimeter or kilometer. So more smaller the size of the pixel, it will be having the high spatial resolution, and if the size of the pixel is big, it will be having the low spatial resolution. This can be understood by this particular diagram. यहाँ पे we can see that the pixel size is 30 meter, in the second one it is 5 meter and in the third one it is 1 meter. And within this 30 meter we are having two objects. One is the house which is having the dimension less than 30 and the red one we can consider this as the barren land. So when we are talking about the pixel output means the sensor which is detecting the radiance from these two objects that is shown as a single object in the output, because if the size of the pixel is 30 meter, it means any object which is having the size more than 30 meter, then only it will be able to identify them as the different object. इसलिए यहाँ पे हमें जो output मिल रहा है that is mainly of the house because majority of the area is covered by this object. So the dominant radiance will be shown here. Likewise, if we see for the 5 meter pixel size, so ऑल दोज एरिया जहाँ पे कोई भी मिक्स नहीं है यानी कि सिंपली हमारा बैरन एरिया है, सो दैट इज शोन हियर एज द रेड आउटपुट. बट इन द केसेस जहाँ पे हमारा मिक्स्ड है जैसे ये रेड एंड द ब्लू अगर हम देखें, सो द मेजोरिटी वन विल बी शोन हियर इन द आउटपुट. सो वी कैन सी हियर दैट इन दिस पार्ट द ब्लू वन इज द डोमिनेटिंग, सो हियर इन द आउटपुट पिक्सल इज ब्लू इन कलर. while अगर हम ये तीनों का देखें जहाँ पे रेड पार्ट इज डोमिनेटिंग, so the pixel output is shown red color. So that is the dominating wavelength or the dominating radiance will be recorded and जो object जिसका dominating radiance है that will be shown in the pixel output. But if the pixel size is reduced, then we can see here that we are getting the accurate information of the house size as well as of the barren area. Sensor will be able to identify two objects as the distinct object only when their sizes is more than the pixel size. Here as we saw that if the size was less than the pixel size, we are not having the clear output. So lesser the pixel size will be having the higher spatial resolution, and if the pixel size is more, it will give us the low spatial resolution. So here we can see four images of the same area. In this we are having the pixel size of 1 meter. Here we can see this is 10 meter, this is 30 meter and this is 250 meter. So we can see that as the pixel size is increasing, the output or the detail of the information which we can acquire from this data or from this image, that is actually getting reduced. Likewise, we have here satellite imagery. This is the fine scale imagery of 2.4 meter and this is of 30 meter. And if we compare these two images, we can see that we can obtain more amount of information from this particular image in comparison to the one which is having the more pixel size. Here we have another example of the Iconos image. One is the panchromatic with the 1 meter spatial resolution and another is the multispectral with the 4 meter spatial resolution. Here again we can see that the level of information is more in the one which is having the high spatial resolution and less pixel size. Next is spectral resolution. Spectral resolution is defined as the ability of sensor to detect the fine wavelength intervals, and it is also defined as the number and dimension of specific wavelength intervals in the electromagnetic spectrum to which these sensors are sensitive. So this is mainly related with the spectral bandwidth. The narrower is the bandwidth, more finer is the spectral resolution. Here we have the atmospheric window diagram showing the wavelength ranges where we are having the maximum atmospheric transmission. So within this atmospheric window, if we are having more number of sensors detecting the narrow wavelength ranges, it will be having the more spectral resolution. Here we have two examples for two satellites. Bottom one is showing for the Landsat 7 and the top one is showing for the Landsat 8. These are showing the number of sensors which are designed to detect the wavelength within this particular ranges. So narrower is the bandwidth. So this is representing the bandwidth. So the narrower is the bandwidth, we are having the more spectral resolution. So within spectral resolution, we have different category. For example, panchromatic, multispectral, hyperspectral, and the ultraspectral. So panchromatic, when the sensor is sensitive for a wider wavelength range. So here we can see this is 500 to 750 nanometer. It means somewhat from the green to near infrared. So the sensor will be detecting all the radiation falling within this wavelength range and will give us a black and white image. Then we have the multispectral in which we are having few bands. For example, here in this one we are having the 4 band. So 0.52 to 0.59 that falls in the green, 0.62 to 0.68 red, then 0.77 to 0.86. So within the visible and the infrared, now we are having the sensors sensitive to particular wavelength range. Here we have two examples. One is of Landsat 7 bands and another is of Landsat 8 bands. So we can see here that in Landsat 8, number of bands are increased as well as the bandwidth has been reduced in comparison to the earlier one. We can compare the bandwidth for the blue. Here it was 0.441 to 0.514, but now it has been reduced to 0.452 to 0.512. So narrower the bandwidth will be having the more spectral resolution. So why this spectral resolution is important? Because the different materials on the Earth's surface, they exhibit different spectral reflectance and the emissivity. So if we are having more number of bands, we will be able to identify different features on the Earth easily. Here we have this example of the spectral reflectance curve and the number of sensors placed on the Landsat 7 which are able to detect in these wavelength ranges. So in the Landsat 7, 5 sensors are there which are able to detect the reflectance in the blue, green, red in near infrared and then shortwave infrared. If wider is the bandwidth, there is chance that some of the objects which are having the similar reflectance, they will not be differentiated easily in the image. So narrower is the bandwidth, we are having the clear quality of the data. So this we can see here that in the multispectral imaging we are having the certain limitation that we are having lesser number of bands and also the bandwidth is more. So here the available information is limited. But when we talk about the hyperspectral and the ultraspectral imaging where we are having 100 to 1000 bands, so more the number of bands, we are having the less bandwidth. From this particular imaging, we'll be able to identify or we will be able to interpret more amount of information because more the number of bands will be having the continuous spectra. Here we have an example, this airborne visible infrared imaging spectrometer which captures the information in 224 spectral channels. So just imagine that if we are having this much spectral channels within the atmospheric window, so will be getting the continuous spectra of different features or objects on the earth. We will be able to identify different features and also their properties using the hyperspectral or ultraspectral data. In multispectral imaging, the images which we get for a single band is black and white image because the sensor is sensitive for a particular wavelength range. So what we get is an image in the black and white shades. So here we have four examples. This is image for the blue band, this is for the green band, this is for the red, and this is for the NIR. As we can see here that different objects have different reflectance in the different wavelength range. So these images of different bands, they can be merged into a colored image using a GIS software. Next is the radiometric resolution, which is defined as the ability of the system to discriminate very slight differences in the energy. ये इमेज हमने पहले भी देखी. Important चीज जो यहाँ पे नोट करने की है कि हम यहाँ पे जो रिफ्लेक्टेंस देख रहे हैं, that is in the many shades of black and white. कहीं पे हमको कंप्लीट ब्लैक दिख रहा है, कहीं पे हमको कंप्लीट व्हाइट दिख रहा है एंड कहीं पे हमको डिफरेंट शेड्स ग्रे के दिख रहे हैं. सो ये विद इन अ पर्टिकुलर बैंड कितनी ज्यादा इंफॉर्मेशन इन टर्म्स ऑफ इंटेंसिटी हम अचीव कर पा रहे हैं, दैट कम्स अंडर द रेडियोमेट्रिक रिजोल्यूशन. जो भी रेडियन सेंसर्स डिटेक्ट करते हैं दैट कैन बी आइदर फोटोग्राफिकली और इलेक्ट्रॉनिकली. सो जो इमेजेस प्रोड्यूस होते हैं उनको हम कहते हैं एनालॉग या डिजिटल इमेज. So aerial photographs are the example of the analog images, while the satellite images which are acquired using the electronic sensors, these are example of the digital image. Digital image is simply the two-dimensional arrangement of the pixels in the columns and the rows. And each of the pixel, it represents a particular area on the earth surface. Now this pixel has two values, one of intensity and second is of the location address. And this intensity, it is given in terms of the digital number. So normally the intensity value, it is the average value for the whole ground area covered in that pixel. And the arrangement of pixels, it describes the spatial structure of the image, while the radiometric characteristics, it describes the actual information which is contained within this image. Each of the band, it gives us a black and white image. The amount of information which is there within a particular image, that is defined by the radiometric resolution. So the accuracy of the digital value or the digital number, it is directly proportional to the bit depth of the device. And this bit depth, it refers to the binary range of possible grayscale values, and it is applicable for the analog to digital converter. Means ये जो information है उसको कितने shades of black and white में convert कर पा रही है. And this value, because the information is stored in terms of digital number, so कितनी ranges हैं, that can be given by the bit depth. अब ये bit depth को अगर मैं calculate करना है, so that is simply 2 to the power of bit that gives us the number of grayscale values. So here in this image we can see if it is 1 bit, it means 2 to the power 1. So we'll be having only two shades. So there will be only black and white. Black will be the areas जहाँ पे complete absorbance हो रहा है and white will be areas जहाँ पे complete reflectance हो रहा है. So if we are talking about the 4-bit system, so 2 to the power 4, that will give us the 16. So it will always start from the 0. So 0 to 15. 0 will be complete black and the 15 will be complete white. So here now we are having total 16 shades of black and white. Now if we talk about the 8-bit system, now 2 to the power 8, it will give us 256 shades of the grayscale values starting from 0 to 255. Now we are having total 256 shades where 0 is representing the complete absorbance and where we are having the 255, it is showing us the complete reflectance. So here it is just a comparison from 1-bit quantization to 8-bit quantization. So we can see that here we are having only two contrasts, black and white, but as we are increasing the number of bit system, the shades are increasing and also the amount of information which is acquired by the sensor, that is also increasing. So higher the radiometric resolution of a sensor, the more sensitive it is in detecting the small differences in reflected or emitted energy. Last is this temporal resolution. Temporal resolution is the time it takes for a space-based platform to complete an orbit and revisit the same observation area. And it depends upon the orbit, the instrument characteristics, and the swath width. So mainly it is applicable for the satellites, because when it is ground based or airborne based platform, we have control over the acquisition of data. But in case of the satellite, as it is continuously revolving around the earth, the revisit time it may vary. So these satellites, they are mainly placed in two orbits. One is the geostationary and second is the polar orbit. This we will discuss in detail in the next video. But यहाँ पे geostationary platforms are the satellites which are at the altitude of 36,000 kilometer and are stationary with respect to the particular location on Earth. So here temporal resolution is final because that satellite, it is giving the continuous coverage of a particular area. But in case of the polar orbiting platform, which are revolving around the Earth at the altitude of 700 to 1000 kilometer, after one revolution, the place on the Earth is little shifted because of the continuous rotation of the Earth on its axis. So after how much time this satellite is again capturing the same area, उसको हम कहते हैं temporal resolution. For example, the MODIS satellite, ये जो है, this captures the same area in every 1 or 2 days. लेकिन जो Landsat series है, they take the image of the same area every 16 days. So now concluding the spatial, spectral, radiometric and temporal. So spatial resolution is with respect to the pixel size. Spectral resolution is with respect to the band. Narrower the bandwidth, finer is the spectral resolution. Radiometric resolution is related to the bit depth. More the number of bits will be having the more number of shades. Temporal resolution is related to the return rate or the revisit time of the orbiting platforms. So there is one question that why not we have such sensor जहाँ पे हमारा सब कुछ अच्छा हो, means we have the high spatial, high spectral and high temporal resolution. So there is difficulty in combining all the desirable features in a single sensor, क्योंकि अगर आपको high spatial resolution चाहिए, then in that case the satellite has to move slowly or the platform has to move slowly. Then in that case जो हमारा temporal resolution है वो हमारा कम होगा. So if the temporal resolution is high, it means जो platform है that is moving fast and is completing the orbit in lesser time, it means हमारा जो spatial resolution है वो हमारा कम हो जाएगा. Likewise for the spectral, if we want the complete acquisition of the information, so the temporal resolution again it will be less. Thus, depending upon the type of data which is needed for a particular study, accordingly the sensors are designed and they are placed on the platform. And from the user perspective, depending upon what type of study you are doing, you can either download freely available data or you can purchase the data from the agencies. This image, it is showing the different spatial resolution and temporal resolution. Here we have the meter to kilometer and the temporal resolution in years. So depending upon the application, we can select the different data. If we want to make the climate study, so less spatial resolution and less temporal resolution will do. But in case of the emergency response, we need high spatial resolution as well as high temporal resolution data. So depending upon the application, we can go for either higher spatial resolution or higher temporal resolution. These are some of the references from where I have compiled the information presented in this video. And if you want to search for these websites, I have mentioned them in the description box. From there, you can refer to these websites. Thank you. We will meet soon in the next video related to the platform.